This is applied physics for undergraduate students, and we are going to talk about the motion in 2 and 3 dimensions. I am Dr. Nasser Majid Mirza. We have already gone through this position and velocity vectors details, but let us recapture the basic idea. If a particle is moving along this path, which is a curved path, and say its position is at P1 at time t is equal to T1, and it goes to P2 position at time t is equal to T2. Then its position vector changes from R1 vector to R2 vector, and the displacement which occurs is delta R. According to the law of addition of vectors, R1 plus delta R will make the resultant vector R2. Therefore, R2 minus R1 will be delta R. And that's how the position vector is used to find out the displacement vector. Let's write down delta R equal to R2 minus R1, and in the component forms x2 minus x1 times I unit vector plus y2 minus y1 j unit vector, and z2 minus z1 k unit vector. The time interval is delta t, and the change in the position or the displacement taking place during the interval is delta r. The average velocity during this time interval is again defined as displacement per unit time, and it is equal to delta r divided by delta t, or r2 minus r1 vectors divided by t2 minus t1. The average velocity is equal to the displacement vector divided by the time interval. Again, the velocity is a vector quantity, and instantaneous velocity is the limit of the average velocity as the time interval approaches to zero. It is this time when it is going to zero, then the velocity becomes instantaneous rate of change of position with respect to the time. And the key difference is that the position r and the instantaneous velocity are both vectors, and the limiting case is delta t going to zero for delta r divided by delta t ratio. And this is the definition of the first derivative. Therefore, velocity is the first derivative of displacement vector r. The magnitude of the vector velocity at any instant of time is the particle's velocity, and the direction of v at any instant of time is same as the direction in which the particle is moving at that instant. During the displacement delta r, the change in delta x, delta y, and delta z can take place in 3-dimensional or 3-dimensional coordinate system. As we have shown here, r is the position vector having all these 3 components, x, y, and z. If we want to write down the velocity vector in 3 dimensions, it is the first derivative with respect to time. So for x component, the velocity x component is vx, and it is dx over dt. Vy velocity component is dy over dt, and vz component is dz over dt. These components are multiplied with the unit vectors respectively, and then we get the total vector. Total vector v is vx times I unit vector plus vy times j unit vector plus vz times k unit vector, and each individual is dx over dt times I unit vector, dy over dt times j unit vector, and dz over dt times k unit vector. The Pythagoras relationship can be used to find out the magnitude of the instantaneous velocity as Vx square plus Vy square plus Vz square under root, and it is shown as V vector's magnitude or simply V. The velocity vector in 2 dimensions can also be written in a simplified manner in which the component along z direction is 0, and therefore the magnitude of the velocity is given as under root of Vx square plus Vy square, and the direction is given by the tangent Vy divided by Vx. Here the velocity vector is shown and its decomposition or breakage into 2 components as along the x and y direction are shown, Vx and Vy, and Vx is making angle theta with the velocity vector V. The angle theta is actually in the positive direction of x axis, and it is a common way of pointing out that it can be decomposed into 2 parts. Acceleration in 3 dimensions, again, is the change in the velocity with the time, and the average acceleration is the change in velocity vector divided by the time interval in which the change in the velocity vector takes place. The change is delta V, and time in which it happens is delta t. Therefore, the average acceleration is given as delta V over delta t. Keep in view that the V is a vector quantity, therefore V2 vector minus V1 vector divided by T2 minus T1, where T2 and T1 are scalar quantities. Instantaneous acceleration, very similar to the instantaneous velocity, is the acceleration when we reduce the time interval delta t going to the limit of 0. So acceleration is the limit in which the delta t goes to 0, the delta v divided by delta t, the ratio, and for this ratio in the limit is calculated and it becomes the instantaneous acceleration. In a sloppy manner, we always declare the acceleration as instantaneous acceleration, and we normally do not write in physics the instantaneous. This above equation is again defining the derivative, and it is a derivative of velocity with respect to time. So here we write acceleration vector is equal to the derivative, the first derivative of velocity vector. The acceleration vector can also be written in 3 dimensions. For example, this figure is showing a curved road near a city, and the vectors V1 and V2 are the car's instantaneous velocities at time t1 and t2, and the car is at point p1 and time t1, and it is at point p2 when time is t2. The 2 velocities can differ both in magnitude and the direction. So during the time interval from t1 to t2, the change in the velocity is delta v, and v2 is basically v1 plus delta v, and we define the average acceleration as the difference of the velocities during the interval delta t. And again, the limiting case is when delta t goes to 0, we have the first derivative of velocity with respect to time equal to acceleration, and both are the vector quantities. We can write down in the 3-dimensional vector form. Velocity vector can be written as a Vxi unit vector plus Vyj unit vector plus Vz times k unit vector, and the derivative of this vector is acceleration. Or we can say that dvx divided by dt I unit vector dvy divided by dt times j unit vector, and the dvz divided by dt times k unit vector is the total A vector, or A vector is composed of 3 parts. Acceleration along x-axis is Ax, acceleration along y-axis is ay, and acceleration along az is along the z direction is az. So in scalar form, we can write the acceleration ax is dv x over dt, d vy over dt is acceleration along y direction, dv z over dt is the acceleration along the z direction. The curved path is a special path in which particle can have always non-zero acceleration, even if the object is moving at a constant speed. Because path is curved, acceleration A always points towards the concave side of the path. Here you can see the acceleration on a curved path as shown. The curved path is this red marked line, and the velocity vector is in this direction. Acceleration is the total vector shown here. It has two components, the radial part and the tangential part. And we can also see that when horses are moving on a curved path, they tilt and they are really tilted towards the concave path, towards the center of the path. Actually, the components of the acceleration are resolved whenever we see the path of the object as a curved path. The acceleration can be resolved into two components. One is the parallel component along the tangent of the path, and the other is the perpendicular or the radial direction. The parallel component tells us about the changes in the particle speed, while the perpendicular component is telling us about the changes in the particle's direction. The effect of the acceleration is basically directed as A parallel to and B perpendicular to the particle's velocity. So this is a velocity vector, and a component which is parallel to the velocity vector is actually the parallel component, which is the path, which is what we call the radial path, and the other is the tangential path. So here we have two components, and here the acceleration parallel to the velocity changes only in the magnitude. V1 plus delta V added together forms the V2, and it is the change in the magnitude. However, acceleration which is perpendicular to the velocity only changes the direction. This is the vector, and the other the V1 vector, and it is changing its only changing its direction, not the magnitude. Since its direction is changed, delta V appears. So particle then follows the curved path at a constant speed. The acceleration basically on a curved path is further needed to be studied. The velocity and the acceleration vectors for a particle which is moving through a point on a curved path with a constant speed, for a constant increasing speed, and for a decreasing speed have three peculiar features. And we need to study these features. Let us go through this one by one. The first graph is showing us in the red color the path traced by the particle. Its velocity vector at position P is shown with a green line. However, normal to this P is A acceleration. When the speed is constant along the curved path, the acceleration points normal to the path. It is always perpendicular to the path. And look at the second P figure. Here again, the red is the trace of the particle's path, and V is the tangent, the velocity, green colored, and the acceleration A is shown here. When the speed is increasing along the curved path, the acceleration is going to point ahead of the normal, it is not exactly at the normal, but it is pointing ahead of the normal. Now, suppose that the speed is decreasing along the curved path, then we have again the paths as shown in the C curve, and we have the velocity as a tangent vector, and the normal to the P is this line, blue colored line. However, the acceleration for this case where the speed is decreasing, the acceleration is pointing behind the normal of the path. So it will be exactly normal when the speed is constant. And if speed is increasing, then it will be ahead. And if speed is decreasing, it will be behind the normal. One very important study of motion is a projectile motion. Projectile motion is where we throw an object, or an object is thrown into the air from certain position, and it forms a projectile. It goes up to certain point and then comes back and falls on Earth. The whole trajectory is very similar to a parabola. However, there are other things to be studied, so we go through this one by one. To study this, let us idealize the projectile motion and its trajectory as shown in this figure, where the y coordinate is pointing towards the positive y is the upward, and the ground is on x-axis from 0 to x, positive values. And when we throw the object, it starts from 0. It makes certain angle, and then its velocity at time t is equal to 0 is v0 vector. Then it starts going up and goes up and reaches a maximum altitude, and then comes back and then follows, and it is dropped here. So the total distance traveled can be termed as a range. Now we consider this model. This model can be a batted baseball. It can be a throwing of a football. It can be a package which is dropped from the aeroplane. It can be a bullet shot from the rifle, and many other cases, all form projectiles. The most important component that we must understand is that the projectile motion is of an object is based on only one force which is acting on it, and it is the gravity. We will ignore air resistance and any drift. We will say that the weather is cool and calm, wind is very, very slow, and therefore the projectile moves only due to the force of gravity. No other forces are present. The path followed by a projectile is called trajectory, and this model is going to be used. Let us brief the model. A projectile is going to move in a vertical plane. This is xy plane. It will contain initial velocity vector at time t is equal to 0, and then its trajectory is going to depend on this v0 velocity vector, and only the downward acceleration due to the gravity, the a here shown. So ax component will remain 0. However, a y component, the acceleration due to the gravity, we will treat as a minus g, because it is downward as compared to the positive y values. So it is showing a decreasing trend in the y coordinate. This model is going to be used to analyze the motion which is represented by the projectile, which is a particle with an acceleration due to gravity, and this gravitational acceleration is constant both in magnitude and in its direction, which is downward, opposite to the increasing y. Here we show a direct free fall or a drop of a ball, which is the red mark, and a projectile, which is at certain angle. It is thrown, and now it is falling, and it is forming a curve. So let us do few properties. Projectile motion is always confined to a vertical plane. It is one plane, X and Y plane. It is determined by the direction of the initial velocity. This is because the acceleration due to the gravity is purely vertical. The gravity will not accelerate the projectile in any sideway direction. So X component of the acceleration will remain 0, and Y component will remain constant and equal to minus G. Here the red ball is dropped from rest, and the yellow ball is projected horizontally at certain angle. These successive images are separated by equal interval of time, and you can see the progression. At any given time, both balls have the same y position, y velocity, and y acceleration, despite having different x position and x velocities. As you can see, the vertical is y and the horizontal is x. We can analyze a projectile motion as a combination of horizontal motion with a constant velocity and vertical motion with a constant acceleration. And we assume that there is no horizontal acceleration. The projectile motion has horizontal motion and vertical motion that are really independent of each other because of the acceleration fact. Neither motion is affecting the other. So the key to analyze a projectile motion is that we are going to treat x coordinate and variable and y coordinate and its variable independent. So let's try. The projectile motion vector relationship for the projectile motion is based on its velocity and acceleration, and we have separate equation for horizontal component and for vertical component, and the component of acceleration can be written as follows. Ax equal to 0. There is no air resistance, no other kind of force, so acceleration along x-axis is 0. Ay is minus g, the acceleration along the vertical direction y is minus g. Since x acceleration and y acceleration both are constant, we can use equation of motion of types that we have already discussed called kinematic equations. So for x part, we write Vx as an initial value of V0x, and from this we can write the position, x position at any time, starting from the x0 position plus V0x times t. And for the motion which is along the y direction, Ay is equal to minus g. Therefore, y part is Vy equal to V0 y minus g into t. And the other equation is y is equal to y0 plus V0 by times t minus half g t square. Here acceleration is minus g, therefore we have substituted the acceleration for the y part. The component for acceleration are given below. Now let us take the origin at the time t is equal to 0 as our starting point. Therefore x0 and y0 are equal to 0, and these equations get simplified. Here I have shown the picture in which the components are being addressed. So let's look at this first. The air resistance is negligible. At the top of the projectile, there is 0 vertical velocity. At this point, it will not go further up. Therefore, its component along the vertical direction, velocity component, will go to 0. It will have only component which is the velocity component along the x-axis. We can see here that the component of velocity are shown for each point here. This is the starting point where V naught is the initial vector, velocity vector. It can be decomposed as V0x and V0y, and both are shown here. The vertical component is a bit more and the horizontal is small. As it goes further, the velocity along the y direction starts going down, and it starts going because of the acceleration downward. This component goes down, decreases. Eventually, it becomes 0. The velocity along the y direction should go to 0, and then it starts increasing, but in the other direction, which is the downward direction, because it is going to fall. So the velocity vector starts increasing, but downwardly, and eventually it falls and hits the ground. Before hitting the ground, the velocity component along the y direction is maximum, and the x component goes to very small value. Now, if we look at this trajectory, it is a combination of the horizontal motion with a constant velocity and a vertical acceleration. So it's a constant vertical acceleration, which is downward, ay equal to minus g, and the vertical velocity is changing by the equal amount during the equal interval of time. Horizontal projectile, we can see the horizontal projectiles is in constant velocity motion. So it's a v naught x, v naught, v1 times x, v2 times x, v3 times x. This is the constant velocity motion, and the horizontal acceleration is 0. So it is making equal intervals in equal time. The x distance is covered in equal manner, and that's how the velocity remains the constant. Because there is no acceleration along the x-axis, therefore this velocity remains constant. However, vertical velocity is changing. It is high first, and it decreases, and eventually becomes 0, and then it changes its direction and keeps on. And this is indicator that there is acceleration, because velocity is changing, the vertical velocity is changing, and it is due to the acceleration minus g that it is happening like this. So very briefly, we write down a simplified component manner the answer. Look at the first part, and briefly let me go to the previous slide. This is the slide in which I have shown the x part of velocity and y part of the velocity. And if the initial position values are 0, x is equal to v naught x times t, and y is equal to v naught y times t minus half gt square. And that's what we are going to use. Here we see that Vx is equal to V naught times cos of alpha naught. This is the initial starting angle. We can write down theta naught also. It is a dummy variable. And x from this we get as V naught x cos multiplied by t. While the motion ay is equal to minus g, y part is then vy equal to v naught times sine of alpha minus g into t, and its integration will lead us to y equal to v naught sine of alpha times t minus half gt square. So these two equations are now telling me the velocity and the displacement component in x direction, velocity, and its displacement components along y direction. I can find out the magnitude of velocity vector and the magnitude of the distance r of the projectile from the origin. And that's what I can write down here. I've written v is equal to under root vx square plus vy square, and r distance equal to under root of x square plus y square. Now, you look at this, if we substitute, we can reduce it, and I have not done those steps. The initial velocity components of the projectile are related to the initial speed, as is shown here, V naught times cos of alpha naught and V naught times sine of alpha naught. Therefore, these components are really related to V naught and alpha naught. And I can shape the equations x and y. This is x equation and y equation. I have here cos of times t, and I can put I can replace the time with this this variable x divided by this. So I get a tangent of alpha naught times x minus g divided by this. So I calculate the time from this equation, t equal to x divided by this, and reduces this whole thing. Now I must not look at the details of this thing, but I should look at the variable. X and y are variables. G is constant, alpha naught is constant, V naught is constant. So let me call them a constant. Here B constant and C constant. So B is this whole thing multiplied by x, minus times this whole thing is C times x squared. So I have this equation. The y component is equal to B times x minus cx squared. And any such equation where the x squared is related to y is the equation of a parabola. So the trajectory, the trace in a x and y coordinate equation is looking like a parabola. If this x squared term was not there, it was 0, then I had a straight line. Y equal to b times x. But it is not straight line, it is straight line minus this thing, which is the parabola. So this equation, whole thing is parabolic equation, which is the trajectory. When I plot on a x and y plot, I get a curve which is looking like a parabola. We will stop here, and we will continue our discussion on this curved path, or the trajectory of a projectile, and how this motion takes place. We have to find out what will be the distance total covered for any angle alpha, and how much time it takes to complete this. So both things are really important and are of value. And in coming lecture, we will do this, and we will worry about the other types of the curved paths as well. We will apply the Newton's law. We have, as you see here, we have already applied the Newton's law. M mass multiplied by A y equal to minus m into g is this. This is the Newton's second law that has been used, and its other component is 0. The force is not there, so it is a constant velocity, or the 0 acceleration along x-axis, but a horizontal motion has a force due to gravity. Thank you so much. We stop here.